Welcome to the lecture on matrices. It's just an introductory lecture on matrices and matrix algebra. We'll learn more and more when we go over a little bit deeper on matrices, okay? So first of all, what is a matrix? Okay, matrix is a natural object, mathematical object, when we're dealing with two-dimensional data. Two-dimensional data. So, of course, this statement does not make sense, of course. So what does it mean, two-dimensional data? Okay, so let's say, for example, that we are looking at the price example, the price of a stock or a commodity stock. Let's say, for example, we want to invest in the Apple stock or IBM stock, whatever, and we are looking at the price versus time, So we can look, for example, on a daily basis, look at a chart, and what we're gonna see is, for example, P1, okay, the price start on a certain date. For example, P1 is the price at the end of the close of the end of the day. P2, the first day, P2 will be the price of the second day, P3 the price of the third day, etc. So this is what's known as one-dimensional data. One-dimensional data. Okay, so if you want to look now at the two-dimensional data, okay, so here, let me give you another example. So this is the first one, and the second one, same, economics. Let's say, for example, we're looking at few families. For the sake of argument, family 1, family 2, and family 3, okay? And we want to look at their expenses in first quarter, second quarter, third quarter of this year. So let's look at, for example, the expenses with respect to housing, food, transport or transportation, and entertainment. Okay, so in this case, what we have family 1. So let's put it this way: family 1, family 2, family 3, and here we put housing, food, transportation, and entertainment. Yeah, so we're gonna have here a number, here another number, here another number, and here another number. So you see, it's a one-dimensional data for what? For family 1. What about if we do it for family 2? We get a different data, okay? As well as family 3. Okay? So here, if I ask you, what is this number? Okay? So this is the transportation expense of family 2 during the quarter, right? Whatever quarter it is that we're talking about. So in this case, clearly, the numbers are given in a two-dimensional format, okay? Two-dimensional format. So we have a two-dimensional data. I mean, it gets complicated. We can have three-dimensional data. This will give us what's known in mathematics as tensors, etc., etc. You can imagine, okay? So if I want to represent this two-dimensional data, what I will do, I will put Q, the quarter, depending on 1, 2, 3, whatever. Let's say, for example, first quarter. And we look at, these are the housing expenses for the 3 families. Then the food expenses for the 3 families. Then the transportation expenses for the 3 families. And finally, the entertainment expenses for the 3 families. So you see, the representation here is what's known as rectangular array of numbers. Okay, so it's natural that, I mean, I can always push it and put them into a one-dimensional data entry, but naturally they are not one-dimensional, they are two-dimensional. Okay, so here in general, what is a matrix? As you can guess, a matrix is a rectangular, it has a rectangular shape, rectangular array of numbers. So to a matrix, we associate 2 numbers. Okay, so here, a remark, to a matrix, we associate naturally, we associate naturally 2 numbers. Okay, so the number of, let me show them to you, the numbers of the columns and the numbers of the rows. Okay, the number of columns and the number of the rows. So here, 2 numbers, number of rows and number of columns. Okay, so in general, we say, for example, A has a matrix. A matrix A has size 2 by 3 if and only if A has, so the first number is the number of rows, 2 rows and 3 columns. Okay, so in general, A has size n by m if and only if A has n rows and m columns. Okay, so in particular, special cases, 2 of them. One, what we call column vector. Column vector is a matrix with 1 column. And of course, similarly, we have what's known as row vector, is a matrix with 1 row. So for example, here, for the case of column vector, is going to be the number of rows, which is n by 1, while here is one row, so it's going to be 1 by the number of columns. Okay? Okay. The concept of square matrix. Okay? So this is the case when the number of rows is equal to the number of columns. So in other words, the shape is not a rectangle but a square. That's why we call them square matrix. Okay? Great. So before we define a little bit more objects associated to matrices, let us make a remark here about very important. So let's say A is a matrix with size n by m. Okay? So in this case, so if n and m are large, just take the case when no, before we do that, let us look at the case of smaller n and smaller m. Okay, so we have A, B, C, D. Yeah? What about, for example, 2 by 3? 2 rows, A, B, C, D, E, F. Okay? 2 rows, 3 columns, etc. So as long as the number, the size are okay, here we can represent it in this fashion, and we do that all the time. Okay, we can even use the Greek letters, etc., etc. But what if we are dealing with economics, like the case of the families, but instead of having 3 families, we have 1,000 families. So you have 1,000 rows. So it is impossible to use the Greek, the Latin letters and the Greek letters and all this stuff combined. So in this case, what we use, we have a trick in mathematics when the number of entries is very large, like we did for what? For linear system or system of linear equations. Okay, so the same here. When the number of entries is very large, then in this case we use the indices. So we use the index notation, like exactly what we did for what? For systems, with large number of unknowns and large number of equations. So we do the same here. So we have A, okay, and we go. So what are the entries? So all the entries, we'll call them by, we'll use the letter A, okay? Because the capital A for the matrix, A for the entries, okay? So we put A. But this is what? The first entry in the first row. So we use A11. So the first one is the row. The second one is the column. The next one will be A12, etc., etc. So what's the last one? This matrix, we said, has n by m size, meaning that n is the number of what? Of rows, and m is the number of columns. So it will be 1m. Okay? The second row will be A21. So this is the second row now, the first number in the second row. And what about A22? Is the second number or the second entry in the second row, etc., till we reach A2m. Now, m columns, the last numbers will be m. So if we go down, So we get, how many rows we said? N. So this is first number in the nth row. So this is AN1. Second number in the nth row, N2, etc. AN. Okay? So this is the general notation that we use. So what about now? Let's look at now, this is the ith column, and this is the row, j row. So we have j row and ith column. So this here, the number that you have here, this here, the entry that you have there, okay, will be A. We said that's the symbol. The row will be the first one, and the column will be what? I mean, okay, what if, because I don't want you to read on the web or something different. What if I replace now, okay, the ith, I consider the j column with the I row. So in this case, we are not going to use ji, but we're going to use ij. So anyway, so I stands for what? The first number stands for what? The first index stands for the rows. The second index stands for what? For the columns. It doesn't matter. So if I tell you, for example, where do you see 521? Okay, A521. That will be the fifth row, the 21st column. Okay, so fifth row, that's the entry that you have in the fifth row and 21st column. Okay, great. So this is all just a little introduction to matrices. We're not doing anything yet. So in general, what we're gonna do is write A to be Aij, like this, yeah? And either we are clear about the size. If we're not clear by the size, we can write Ai less than N, J less than M. So N is the number of rows and M is the number of columns. If we know the size of the matrix, then we don't need to do that, because we know that the first index I represents the rows and the second index J represents what? The columns. Okay, great. So now what happens when a matrix is a square matrix? Okay, so in this case, what we see here is a square. So what do we have? We have A11, A1n, A21, A12, A22, A2n, and N1, AN2, and ANN. Okay, so because it is a square, so let me just make a little drawing here. Okay, so this is a square. Okay, so for a square, you have this here is known as the diagonal. In fact, a square has two diagonals. Okay, this is the first one, and then you have the other one, which is this one. Okay, so there are two diagonals. Okay, so in the case of a matrix, this here, what you see here, is what we call the main diagonal. We do have the other diagonal, but the green one that you see there is the main diagonal. So what are the elements on the main diagonal? Okay, so the main diagonal of a matrix, is given by given by the numbers A11, A22, etc., ANN. This is for a square matrix, okay? It's very, very important because it plays a major role, the main diagonal in the study of matrices, okay? That's why, okay? So keep in mind, we're looking at the numbers A11, A22, ANN. In other words, we're looking at when the indices are both the same. So now we can say a little bit more about matrices, but let us stop here and now see some of the basic properties of matrices. And remember what we said. We said we're dealing with introduction to matrices as well as what? Matrix algebra. So we want to do some properties of matrices. So let us start with the first one. What does it mean that A, so first one, okay, what does it mean that two matrices are equal? Okay, equality here. Okay, so we have A equal Aij, B equal Bij, and we are talking about the same size. Two matrices, they have to be equal, they need to have the same characteristic, the same information. So they have the same size. Both of them are the same size, n by n, for example. So what does that mean that A is equal to B? This means that all the entries are the same. Aij equal Bij for any I and J. Okay, so all the entries are the same. Okay. 2. In order to understand 2, let me go back to the example of the families. So we have quarter 1, which is, okay, we have A11, okay. So remember, that was the housing expenses for family 1 in that quarter, okay. Then we have A 1 2 1, because 2 is the row and 1 is the first column. So A21 is family 2 expenses for housing, okay. A31, and then we have what? A1 2, A22, A32. So remember, these are the expenses for food in that quarter. Okay, and then we have what? A13, A23, A33. And then we have what? These are expenses for transportations. And finally, the entertainment. A14, A24, and A34. Okay, so now let us do the same, but for second quarter of the year. Okay, so we're gonna have Bij for the second quarter. What if I ask you now, okay, to find, so the first quarter is added to the second quarter, it gives me the first half of the year. Okay, so let's say expenses for the first half of the year, and let's call it H1. Okay, so what we are going to do is the expenses for every item. Okay, for example, family 2, food. Okay, food expenses for family 2 for the first half of the year will be the expenses in the first quarter added to the expenses of the second quarter. So the answer will be A11 plus B11, etc. Okay, A12 plus B12, etc. A13 plus B13, etc. and A14 plus B14. Okay, so here, for example, it will be what? A 3, 2 plus B, 3, 2. So you just add them basically. You add them all. Okay? So what did we do? We took every entry in the first quarter, added to every entry the same. Okay? So this is known as addition of matrices. Okay? So what do we have? We have A equal Aij, and we have B equal Bij. Okay? And in order for us to add them, they have to have the same size. Okay? And they have to have the same size. So A plus B will be Aij plus Bij. That would be the addition. So of course, we can ask, is there a matrix that behave like the zero number? Okay? And the answer is yes. We have what's known as the zero matrix. So this is, we put it like this. So all of the entries are equal to what? To 0. If you take, obviously, A equal Aij, okay, then A plus the zero matrix will be Aij plus 0, because all the entries are 0, which is Aij. So you see, in other words, A plus the zero matrix is equal to what? To A. So the zero matrix behave exactly the same as the zero number. Keep in mind, we don't have just one zero matrix because it depends on the size. For example, we can look at 0, 0, 0, 0. So this is the zero matrix with size 2 by 2. In other words, a square matrix. But we can have also 0, 0, 0, 0, 0, 0, 0. And this is the zero matrix with size 2 by 3, etc. So we have different what? Zero matrices depending on the sizes. So now, remark. Let us look the case when you have Aij and we want to add A to A. Sorry, A to A. Obviously, we can do that because they have the same what? The same size, okay? So this will be Aij plus Aij. But we know from numbers, real numbers, that if you add the same number, it's like multiplying by 2. Yes? Right? So basically, this looks like A plus A is like 2 times A. So we are multiplying the matrix A by the number 2. And what is the end result? The end result is to multiply every entry by 2. So for example, if we take 2 times A, B, C, D, then the end result is 2A, 2B, 2C, and 2D. Okay? So this suggests the following, which is known as multiplication of a matrix with a number. So here we can say, for example, lambda times A. A is a matrix and lambda is a number. So this is lambda times Aij, the matrix defined by the entries Aij. It doesn't matter the size, by the way. And this would be, the answer is lambda times Aij. So we multiply all the entries by lambda. It's very important because when we go to the concept of determinant, things gets a little bit more complicated. Okay? So in particular, what is 0 times a matrix? It's going to be 0 times Aij, which is 0 times Aij, which is the zero matrix. So the number 0 times any matrix will give us what? The zero matrix. Okay? So for example, just for the sake of, okay, if I give you A equal 1, 2, 0, minus 1, and B equal 1, minus 1, 3, 2. So these are both of them 2 by 2, in other words, square matrices. Then if I multiply A by the number 3, and I add 2 times B, I can do that. Why? Because 3 times A will be a 2 by 2 matrix, 2 times B will be a 2 by 2 matrix. Therefore, 3A and 2B, they have the same size, and I can add them. So what do I get? I'm going to take all the entries of A and multiply them by 3. I will get 3 times 1, 3, 3 times 0, 0, 3 times 2, 6, 3 times minus 1, minus 3, plus 2 times 1, 2, 2 times minus 1, minus 2, 2 times 3, 6, 2 times 2, 4. And then I will add them to find 3 plus 2, 5. That's the first entry in the first row, first column. 6 plus 6, 12. 0 minus 2, minus 2. And minus 3 plus 4 plus 1. And that's the end result. Okay, so this will help us now, application. Let us look at the case of linear systems. So system of linear equations. So what do we have? We have A11 x1, the general form, of course, A12 x2, A1n xn. If we assume that n is the number of unknowns, equals B1. Second equation, A21 x1, A22 x2, A2n xn equal B2. And if we assume that we have m equations, A m1 x1, A m2 x2, A mn xn equals bn, the last equation. Okay? So, in this case, what we have, I can write, using the equality, the following. Look at this now. I'm going to play using the matrices. I'm going to play with this. So it's going to be A11 x1, A12 x2, plus A1n xn equal, and the first entry is equal to B1. Okay. Now, the second row, A21 x1, A22 x2, A2n xn equal B2. And then if we go down, the last one will be AM1 x1, AM2 x2, AMN xn equal Bn. Yes? Good. So now let us use the properties that we just learned. Not fancy yet, but just the basics that we learned so far. So we have what? A11 x1, A21 x1, etc. plus A12 x2, A22 x2, AM2 x2 plus, and the last one will be A1n xn, A2n xn, AMN xn equal B1, B2, Bm. Okay, so now we use the properties of, we use the addition, but now let's use the properties of what? Of multiplication by number, and we can take x1 outside, okay? And usually when you multiply a matrix with a number, you put the number to the left and the matrix to the right all the time. It's a convention, okay? So we put x1 times A11, A21, AM1 plus x2, A12, A22, AM2 plus xn times A1n, A2n, AMN equals B1, B2, BM. Okay, so what are these? Okay, so if you take the coefficient matrix, not the augmented matrix, not the augmented matrix, the coefficient matrix of the system, the coefficient matrix. Okay, so what we have so not the augmented matrix, not the augmented matrix, is the coefficient matrix. So we have A11, so the first column, the first row, sorry, A11, A12, A1n, A21, A22, A2n, and the last row will be AM1, AM2, AMN. So remember, the rows are exactly the number of equations, which is n being what? The columns being the number of unknowns. So what's interesting is, if you look at here, what do you see? Okay, so look at this one. Okay, that's the first what? Column. Okay, and if you take this one, that's the second column, and the last column is this one, sorry, and that's the last column. So what you see there are the column vectors of the matrix A. That's what you see. So usually we call them, so we call this one A1, this is A2, AN. So we call them, these are the column vectors of the coefficient matrix A. So what we have in this case, the equation that we just saw right here, it becomes x1, A1. So remember, A1 is the column vector, the first column vector of the matrix A. x2, A2, etc., xn, an, and this is equal to what? To B, the non-homogeneous column, which is B1, B2, B1, B2, Bn. Okay? So these are vectors. So here, so a little terminology. So what you have here, okay, a little terminology, I mean just terminology. So we say that B, I'm gonna write it here, B is a convex because, is a linear combination of the column vectors of the coefficient matrix A. Okay, so the column vectors are A1, A2, AN, and B is a linear combination. Okay, so you have a solution if and only if. So we have this result now. Okay, we have this beautiful result. So the system is consistent, which means we do have a solution if and only if the non-homogeneous term B, B1, B2, Bm, is a linear combination. It's amazing combination of the column vectors of the coefficient matrix A. So this is all like a little bit of simple stuff. And now what are the new concepts? that we learned in this lecture. Okay, so what we learned is, number one, what is a matrix? Okay, the definition of a matrix. Number two, what is equality of matrices? Number three, we talked about addition of matrices. 4, multiplication by a number, multiplication of a matrix and a number. Usually we say scalar. And finally we talked about the concept of linear combination, when we combine addition with multiplication by a number.